Dear students, today we are going to discuss about three topics. One is the electromotive force, then next is the what is electric power, then finally we will learn that what is the heating effect of electric current when it flows through a conductor. So students, let us start. Electromotive force, actually the name force was given to it in the sense that something is there which is causing the charge carrier to flow from one terminal of the cell to the another terminal of the cell, as was seen by Michael Faraday. But it is not a force at all. That we have to bear in our mind. It is what it is. It is work done per unit charge in moving it from one terminal, that is say you are moving positive charge. So in moving positive charge from one terminal to the another terminal, that means you are depositing some unit positive charge from negative terminal of the cell on the positive terminal of the cell. So whatever amount of work done per unit charge, that is called electromotive force. Means whatever amount of work we have done in doing so, depositing the charge on the terminal of the positive terminal, positive charge on the positive terminal of the cell, that amount of work done will remain in the form of energy per unit charge. So that is electromotive force. It is not a force. You have to always bear in your mind work done in bringing unit positive charge from negative terminal of the cell to the positive terminal of the cell, where the positive charges are deposited. So positive terminal. Now it is also equal to the potential difference between the two terminals of the cell when no current is drawn from it. When the circuit of the cell is open, whatever potential difference exists between across the two terminals of the plate is equal to the electromotive force of the cell. And mathematically we write total work done by total charge taken charge to be infinitesimally small. So the SI unit of electromotive force is Joule per Coulomb UC, Joule per Coulomb UC, or we can also call it Joule per Coulomb as volt. So EMF is a scalar because we have defined it as work done by charge. Work is a scalar and charge is a scalar, so it remains a scalar. So that is electromotive force. Next is electric power. We define electric power as the rate of work done, and since work done and energy are equivalent, heat energy may be other form of energy. So we from the work energy theorem we understand that we know that work and energy are equivalent terms. So we also write work done by time or total energy delivered by time or heat produced per unit second or total heat produced by total time taken. All are equal to the power, that is the rate of work done, and or rate of energy supplied, rate of energy consumed, rate of heat produced. So same thing. Now we know, according to the definition of work done in terms of potential, you have already learned earlier that potential V is equal to amount of work done per unit charge. You bring the unit charge from infinity to that point, and whatever amount of work done you do per unit charge, that is electric potential. And from this definition you have V is equal to W by Q, therefore W is equal to QV. So for power you can write instead of work done you can write QV by T. And you also know that Q by T is nothing but current, total charge flown per second, that is current. So you have power is equal to VI. And students, you can remember it in terms of some common language, that power is very important. You see, power is very important. So that way you can memorize it. And since power is equal to VI, and we all know according to Ohm's law, V is equal to IR. V is equal to IR, so we can substitute the value of V or the value of I in the given expression to have different form of power, expression for power. You see V is equal to IR, therefore we have I is equal to V by R. So you select what you have to do. If you are replacing this I, then I is equal to V by R. So that means you write V by R into V, that becomes V square by R. So this is another format for the expression for power. Why we are talking about these formats? Because at times you will see that you have the available data in terms of voltage or current, or in terms of only voltage and resistance. So or in terms of later on you will see current and resistance. So what data is available, we will opt that type of expression which suits us. So that way we have found the second form of the power, second expression. Now we can find yet another form. You see V square by R. Now if you replace this V by IR, so you get V square R, that means I square R square. I square R square divided by R becomes I square R. So that is the third form of power. Power is I square by R. So the power is a scalar, you see, because power is work done per unit time, that means it is a scalar, and its SI unit is joule per second, because work done by time, that is joule per second, and we also call it joule per second is called as watt. So this is all about power, and so you simply need to remember one form of the expression for power, and you can derive the other two very much easily. Now third topic we are going to learn is Joules law of heating, which you can see can be derived directly from this definition of power. Power is equal to heat upon time, and power is equal to I square. So that means you can write heat produced is equal to I square RT. You see, I square RT. This is the expression for heat. But Mr. Joules did the experiment and empirically found that heat produced through a conductor is directly proportional to the square of the current flowing through it, and is directly proportional to the resistance of the conductor, and directly proportional to the time for which the current was allowed to flow through the conductor. So that means these are proportional relations, these are having proportional relation with the heat produced, and writing all these together, taking the proportionality constant as 1, we get H is equal to I square RT. Now again we can write this heat produced in another format. For I square R we can write V square by R. So for I square R we write V square by R into T, and for I square R we can also write VI. Therefore H heat produced is equal to I square RT, or V square by RT, VI square by R into T, or VIT. So this is in this way we can find the heat produced in three different formats. All depend what data we are available to us. We use that expression to make the job comfortable. So that's all for today. Thank you and have a nice day.